Now let's look at some examples where we can use the integral test. To begin with, suppose we have the sum from k equals 2 to infinity of 1 over k natural log of k. Notice that the terms of this series would go to 0, so we can use the test for divergence. It's not telescoping, it's not geometric, and so really it kind of rules out what we've seen prior to this integral test, but it turns out that we can use the integral test. Notice that this series starts at k equals 2. We talked about how the starting point does not matter in terms of being able to use the integral test. Here, it would not be able to start at 1 because we would have natural log of 1, which is 0 in the denominator. So once I notice that my terms, 1 over k natural log of k, those terms are always positive for k equals 2 to infinity. They're decreasing. And if I construct the associated function, that would be continuous on those values. So I can use the integral test, and I'm going to choose to integrate over the same bounds. And my associated function is simply what we get when we replace those k's with x's. So this, in the statement of the integral test, this would be our f of x. And like I said, importantly, we can apply this because f is positive, continuous, and decreasing on the interval from 2 to infinity. Now, this is an improper integral, and that means that we need to take the limit as b approaches infinity, for b being our upper bound of integration. Notice that I can use a u substitution here. If I were to let u equal the natural log of x, then du would equal the 1 over x dx. And also, if x is 2, then u would be the natural log of 2. And if x is infinity or heading toward infinity, so is the natural log of x. So we get that that upper bound is infinite as well. So I can interpret this as the integral from log 2 to b of 1 over u du. So this now becomes the limit as b approaches infinity of the natural log of u, natural log of the absolute value of u, evaluated from natural log of 2 to b. So what we're left with is the limit as b approaches infinity of the natural log of b minus the natural log of 2. And it's this part that's problematic here. As I send b to infinity, that's going to go to infinity. So we find that the integral does not approach a finite number. Consequently, the integral diverges. And what the integral test then says is that the series behaves the same way. So consequently, the original series that we're looking at, that of 1 over k natural log of k, this diverges. And like I said before, we need to justify why it diverges. And of course, much of my justification is evaluating that integral. But I want to reference what test. So this is going to be by the integral test. And we can use for shorthand reference here by IT. We're not going to have any other tests that have that association. So there I've shown a complete solution where I've fully justified that that's going to diverge. Let's look at another example. And this is going to be looking at series of the form, the sum from k equals 1 to infinity of 1 over k to the p. We, from here on out, will refer to these as p series. And what we said before is we've seen that the integral from 1 to infinity of 1 over x to the p converges when p is greater than sorry, this is strictly greater than 1, and diverges when P is less than or equal to 1. We're going to be able to use that conclusion to say something about these series. Now we have to be a little bit careful here. The 1 over k to the p is only going to be decreasing when p is greater than 0. So technically, I could only use the integral test to make a claim that the series is going to converge for p greater than 1 and diverge for p between 0 and 1, inclusively with 1. But we'll get the other part. So if p were negative, so for instance, 1 over k to the minus 2, right? That would just be k squared. If p were a negative value, we would be able to show that the series diverges by the test for divergence. So technically, if those terms are increasing, we couldn't use the integral test, but we would still get the same result because of the test for divergence. So that's a long-winded way of kind of putting that together to say that we're going to be able to have here a general conclusion for p series, so anything of this form. These converge when p is strictly greater than 1 and diverge when p is less than or equal to 1. And that's going to be a really important fact to remember because we'll be able to quickly make that conclusion about any series that looks to be a p series. The other thing I want to mention at this point is we've talked about the harmonic series very briefly. So as a good counterexample. So the harmonic series, if you recall, this was the sum from k equals 1 to infinity of 1 over k. This is a p series with p equal to 1. And now we can see that this p series diverges by the integral test. So when we talked about the harmonic series before, we said that this was a classic example of a series whose terms approach 0, and yet the series still diverges. When we spoke about it before, we could not justify that that series did in fact diverge. And here we see that the integral test would give us that because the integral from 1 to infinity of 1 over x would diverge as well. And then finally, the other thing I'll point out here is another kind of warning. Be careful with p series and geometric series. These are often confused, I would say, because of course there's some kind of similarity in their presentation, but think about what's different. So for p series, there's an index in the base and the exponent is constant. For geometric series, our traditional form is r to the k. We have a constant base and the index is in the exponent. So while these may look similar, we have to be very careful because the way in which we handle these is of course different and leading to different potential conclusions. Okay. Another thing to consider at this point is that the integral test, when we can use it to show that a series converges, importantly, it does not give us the sum of the series. So that's something special about using our definition directly. if a series converges and I can find the limit of its partial sums, that actually tells me the number to which it converges. Here, we don't have that same result. And to better convince ourselves of that, we can actually look at a particular example. So if I have the sum from 1 to infinity of e to the minus k. Importantly, the function f of x equals e to the minus x is positive, decreasing, and continuous, meaning that we could apply the integral test here. So doing so, we would look at finding the integral from 1 to infinity of e to the minus x. That would be, again, improper. The antiderivative would be minus e to the minus x. And if we plug in b and take the limit here, notice that e to the minus b, as b heads toward infinity, will go to 0. So we're going to be left with 0 minus a negative, so plus e to the minus 1. So this means the series converges by the integral test because we've shown that the integral converges. However, it turns out it does not converge to e to the minus 1. So there are a couple ways we could see that. Notice e to the minus 1 is simply the first term of the series. But moreover, we can actually look at the fact that this sum is actually a familiar type of sum. Turns out this is geometric. To see that, we can rewrite this. So this is 1 over e to the k. And further, I can write that as 1 over e all to the k. So this is geometric with the r value, an absolute value, being 1 over e. So that's less than 1. So we would be able to see that it converges using the fact that it's geometric, but also the sum of this geometric series from our formula that we derived before is the first term divided by 1 minus the r value. So notice that's e to the minus 1 over 1 minus e to the minus 1. That's not equal to the value of the integral. This would be the true sum of the series, and we see that's not the same as the integral. So the integral test is really, really useful, and it's really powerful for letting us see that a series converges. But what we don't get from that is knowledge about the sum of the series. And in this case, we were able to still find the sum because it was geometric, but we're going to encounter a lot of examples that we can show converge using the integral test, and we really don't have another means for finding the sum of the series. What we'll get to later is that kind of the next best thing is, if I can't sum the series exactly, trying to approximate the series and hopefully coming up with some kind of bound on the resulting error. It turns out we will have a way to do that when we're using the integral test.